In this lecture, we'll just give the introduction to the digital filter design. Okay, so in digital filter design, whatever so far we have discussed or introduction to the digital filters, we have we have just discussed several basic filter architectures, and we have classified based on the length of the impulse response. And these two categorization, based on this categorization, we have an FIR filter and IR filter, finite impulse response filter and infinite impulse response filter. Okay, so we have infinite impulse response filter and the finite impulse. We've also classified the filter based on the magnitude response. Okay, here we have seen a low pass filter, high pass filter, we have seen a band pass filter, and similarly we can have a band stop filter, and a filter can be all pass filter, and comb filter is where we have multiple pass band. Okay, in the high in the band pass we have only single pass band. However, in the case of a comb filter we have multiple pass band. So we have I had shared you the slides related to the comb filter and the all pass filter, which I had not discussed in detail in the previous lectures. Anyway, so now the other one is categorization is based on the phase response of the filter or the system. We have seen a zero phase response filter, we have seen a linear phase, and we have discussed the importance of the linear phase, where I told you that that's a desirable requirement. If the system is a linear phase system, all different frequency component will experience the same delay when passing through the system or the filter. So at the output, the output signal will not contain any phase distortion. Okay, so it is necessary to have a linear phase filter in order to avoid phase distortion for a real-time application. Okay, zero phase is also not introducing any phase distortion, but it cannot be realized for causal system. And the generalized linear phase system is there, and the non-linear phase is there. So this is also a linear phase. However, the non-linear phase will cause distortion. Okay, so in the FIR filter, so far we have seen the first order moving average filter. We've taken an example of a low pass filter, first order moving average low pass filter, and we have discussed that filter. And then we have seen a first order high pass filter, means we can obtain a low pass filter, we can obtain a high pass filter from a low pass filter by just replacing Z with minus Z in a moving average filter. We have seen that. We have seen the cutoff frequency. We have seen the magnitude response after replacing Z with minus Z and all those things in the previous lecture. And then we have also seen the high order FIR filter can be obtained if we are cascading different lower order filters. Suppose if we want a high order filter, say order of 3, what we can do, we can cascade this first order filter, okay, and 3 times, so we'll be getting order 3 FIR filter. And the other thing which we have observed, by increasing the order of the filter, the transition width is decreasing, which is a desirable. Actually the transition width should be 0 ideally, but we have seen that is not practically feasible. Means those kind of system cannot be practically implemented. We have relaxed the characteristics of the filter. And anyway, so we have seen, so because of that we have some finite transition bandwidth, but this transition bandwidth can be decreased. Finite transition bandwidth can be decreased if we are increasing the order of the filter, and we have seen an example for this in previous lectures. Okay, the same thing can be applied for the IR filter. Whatever we have discussed for the FIR filter, the same thing can be applied for the IR filter, and which I had not discussed in the video lecture, but I had shared some study material related to this. and as well as I had shared a related study material related to minimum phase and maximum phase system. So this part you have to do yourself. Okay, let me clear this. And so this part and this part you have to do yourself. I had already shared the study material for this. Okay, now the transfer function the transfer function provides for these are fixed. Whatever we have discussed, we have seen a fixed transfer function. When we have a fixed transfer function, it means we have fixed coefficient. It means it does not allow, or there is no flexibility in the design of the filter if the coefficients are fixed. Whatever we have seen in the FIR filter, we have seen the coefficients are fixed. Whatever we have I had shared with you for the IR filter example, we have seen the coefficients were fixed. But actually, we need to have some flexibility. Means we can change the filter coefficients. Okay, so once we have picked the structure and order of the filter and all filter specification can be a pass band gain, stop band gain, cutoff frequency, okay, all those things. So if all these things are given to us, including the cutoff frequency, can be automatically determined. So basically the designing part of the filter, okay, with given specification, okay, or basically designing a filter with desired passband and stopband characteristics, okay, so is nothing. This problem is called basically filter design technique. Okay, how to design a filter with specific desired passband and stopband characteristics. Okay, so this question is answered, basically answer is design filter using different techniques, which we will be discussing in in the few other lectures actually. But here in this lecture we are just giving introduction to this. Okay, so come to the filter design. Okay, so the objective of filter design is obtain a realizable implementable transfer function which approximate the desired frequency response. Desired means the specification which are given to you. As I told you in the previous slide, the specification pass band and stop band specification are given to you. What you have to do, you have to, based on those desired frequency response, you have to implement a realizable transfer function. Okay, so the best place to do is in the frequency domain basically. So based on the frequency characteristics we can do this. Okay, and generally the filter design in where the frequency domain operation are most beneficial. Okay, so basically now what is a digital filter design? It's a process of deriving these transfer function, okay, the realizable transfer function which will satisfy the desired frequency response. Okay, so typically the magnitude response of the desired frequency is specified. Generally when the specifications are given, they give the magnitude response, okay, of the filter. Sometimes they also provide the phase response. Okay, so in the frequency domain, let's recall there are four basic types of ideal digital filter, like a low pass, high pass, band pass, okay, and band stop. So we have the first one is the low pass. You can see it's from given from minus pi to pi, and obviously these all are symmetric magnitude response. All of these high pass, band stop, and band pass, all of these four types of digital filters have symmetric magnitude response with respect to vertical axis. Okay, so here you can see this is the WC. Omega C is the cutoff frequency for this low pass filter, and here omega C is the cutoff frequency for this high pass filter. In the case of band stop, there will be two cutoff frequencies, omega C1, omega C2. Similarly, for the case of high band pass filter, there are two cutoff frequencies, omega C1 and omega C2. Remember, the maximum frequency is pi and the minimum frequency is minus pi. Even if, since the impulse response of these filter will be a real valued impulse response, it's we can just show only the positive side of the magnitude response, which is sufficient. The spectrum is given from 0 to pi, that is sufficient for us. These are the sufficient specification. Similarly, for this also we can just specify from 0 to pi. Same for this, specify from 0 to pi, and for this also we can specify from 0 to pi. Okay. Okay. So, however, these four filters cannot be realized because they are ideal filters. Okay. Okay. So, if we want to realize these ideal filters, I mean, these kind of filters, we need to relax, okay, or smooth the sharp filter characteristics. So you can see there's a sharp change, high, and there's a sudden drop in the gain, you can see, you can follow my cursor. Okay, so this is not these are the ideal brick wall structure filter, but that cannot be realizable, which we have already discussed mathematically also. So so what we have to do, do some smoothing of these structures, basically, or these shapes actually. Okay, so smooth we'll just do, that's why they are saying relax the sharp filter characteristic in the pass band as well as in the stop band by providing some acceptable tolerance. We'll discuss this, means what is the tolerance and all those things, the next slide. Okay, so let's move to the next slide. Okay, filter specification. I use a word, means filter specifications are given to us, and the filter design job is, means give calculating the coefficient of the filter is nothing, it's a designing a filter, and the calculation of these coefficients are based on the filter specification. Okay, so the filter design is nothing, it's a calculation or of the filter coefficients, and the calculation of these coefficients is based on the specification of the filter. Okay, so here is the basically you can say the relaxed magnitude response of a low pass filter. You can see relaxation is given in the in this pass band. It allowed the variation or the minor variation in the gain in the pass band. So ideally it should be 1, but it can vary from minus delta p to positive delta p. The other thing, in the stop band, you can see the gain is not 0. However, we have seen there is some fluctuation in the gain, and that gain, the maximum value of that gain is delta s, stop band gain, maximum stop band gain. The other thing, deviation of this from the ideal filter is the transition width. You can see that this transition width is not equal to 0, which was the case of an ideal low pass filter. So these are the relaxation which we have to give in the pass band, in the stop band, and the transition band. Okay, so here the omega p is this is the omega p basically. This is the pass, we call it pass band edge frequency. You can just map it from here. Omega s is the stop band edge frequency. So this side we have, on the right side we have stop bands, so we call it stop band edge frequency. On the left side of this we have a pass band. The left side of this omega p we have a pass band, so we call it pass band edge frequency. Delta p, so this is called peak ripple value in the pass band. So in the pass band, this is the maximum rippling which is allowed, so that's why we call it delta p is a peak ripple value in the pass band. Delta s is the peak ripple value in the stop band. So the maximum ripple which can occur, maximum gain you can say in the stop band, that is delta s. Okay, so in the case of ideal filter, we know that the magnitude response should be equal to 1 in the pass band. However, in the case of this relax filter, the magnitude response is approximately equal to 1. Okay, where we can tolerate an error of plus minus delta p. Okay, this is some tolerance is there, we can tolerate the error. So that's a tolerance which we were talking in the previous slide. Okay, so there is a minor tolerance which we can accept actually in the case of practical filter design. Okay, so then we can say the gain can lie from 1 minus delta p to 1 plus delta p. Okay, in the pass band, that's a pass band. Okay, mod of omega is less than omega p is nothing, it's omega from minus omega p to omega p. Okay, the next thing is h e power j omega. So the mod of this is approximately equal to 0 in the stop band. Basically in the stop band, actually ideally it should be equal to 0 in the stop band, but in the case of realizable filter we are saying approximately equal to 0. There we can tolerate an error of delta s plus minus delta s. Since this is a magnitude response, so we can say so you can say the maximum is delta s, but it can be plus minus delta s, so we can tolerate this part. Okay, so now the mod of h omega should not be equal to 0 but should be less than equal to delta s for omega from omega s to pi, as well as from minus pi to minus omega s. Okay, so these are some basic filter specifications which is given for which can be given for designing a filter basically. And these filters are only these kind of filters basically can be realized. We cannot realize an ideal filter. Okay, okay, till now whatever we discuss, we will assume that we are dealing with filters with real coefficients, means the impulse response of the filter is a real valued function. Okay, if the function is a real valued function, then the Fourier transform of that function, that is called a frequency response, is a periodic function of 2 pi and symmetric around 0 or pi axis. Okay, so that's the thing I told you, that if the signal is a real valued signal and you go in the frequency domain, so that in the frequency domain that signal that discrete time signal, if you have, I'm again repeating, a discrete time real valued signal. Okay, if you take its Fourier transform using DTFT, discrete time Fourier transform, so that will be periodic with a period of 2 pi, and it will be symmetric, the magnitude response will be symmetric across the vertical axis, or you can say for the axis omega is equal to 0 or omega is equal to pi. Okay, so these were the filter specifications. We move to the next Okay. Okay, one more thing. Sometimes we can specify uh, in terms of these gain in terms of basically in decimal unit basically, or in terms of loss. So here the g omega term is defined, which is nothing, which is minus 20 log of magnitude response to the base of 10. Okay, since minus sign is there, so it's a loss basically. That's what they're saying in terms of loss. So that's nothing, that's a magnitude response we have taken, and taken the log of magnitude, we have taken the log of that and then multiplied by minus 2. And these there's another term with peak pass and minimum stop band ripple. Okay, so basically we have a term alpha p, which is equal to log of 1 minus delta p to the base 10 with minus 20, and alpha s is again log of delta s to the base 10 with minus 20 factor. Okay, so that's one thing. Now, sometimes the specification of the filter can be given in a normalized format. Here it's normalized in the way the maximum value is 1, and it's going, the minimum value of the in the passband gain is 1 by under root of 1 plus epsilon square. So and delta s is given by 1 by a. So this is the main thing actually. It's a normalized to 1. Here it was 1 plus delta p. So this one is normalized. So the whole gain is divided by 1 plus delta p. So in that case, so this part means 1 by under root 1 plus epsilon square will be equal to 1 minus delta p divided by 1 plus delta p, and 1 by, and in this point basically 1 by a will be equal to delta s divided by 1 plus delta p. Okay, now that's why they're saying the magnitude specification can also be given in normalized form. Okay, when the maximum passband value is normalized to 1, you can say the maximum value of the passband was 1 plus delta p. Now it is normalized, you can see here it is normalized to 1. Okay, then we have maximum passband deviation and maximum stop band deviation, which is given by these two things. This is a passband deviation and this one is the stop band deviation. Okay, move to the next. Few important points which you should remember. If the filter is an FIR filter, okay, then its system function or hz is a polynomial of z inverse with, and it's a polynomial with the coefficient of this z power minus 1 with real coefficients. Okay, so hz will be equal equal to something like, we have taken the z transform of some sequence, that is a bn sequence. So here we have taken the z transform, and which is equal to this. Okay, if linear phase is desirable for this kind of filter, if the linear phase is desirable, then I told you the filter coefficient bn or hn. Let's change the color. Bn, this sequence is a filter coefficient, and that's, or we can call it hn. It's an impulse response or the filter coefficient of an FIR filter. So for the filter to be a linear phase, okay, so the impulse response or the filter coefficients must satisfy this property. which we have already discussed. Just you should keep this in mind actually. Okay, so it's a symmetric impulse response, you can say symmetric or anti-symmetric. If the positive sign we are considering, so it's a symmetric. If the negative sign we are considering, then it is anti-symmetric. uh, However, see, we've seen this defining the order of the filter, and is defining the order of the FIR filter. Larger number of coefficients means better will be your filter is going to meet the specification in a better way. But we need to limit the order because of the computational limitation. So our design should be computationally efficient basically. Because if you have a filter, you are doing your input signal is coming to the filter, so the filter is just filtering, producing some output based on some processing, and that processing basically filter is doing nothing. Filter is convolving the input signal xn with the impulse response hn. So the number of multiplication and addition required when you're doing convolution between xn and hn is depending on the number of samples available in hn. If the hn is having large number of samples, so in that case we need large number of multiplications and additions. Okay, so that will not be efficient. So efficiency is in that sense actually. So for computational efficiency, the minimum filter order m should be selected that satisfy the design criteria. Okay, it's not okay you can take any value of n. Take the value of m, minimum value of m, which will satisfy the design requirement. Okay, if you are taking a larger value of m which is not desirable, so obviously you are increasing the computational complexity, because hn will be of larger length, large number of samples will be there in hn. And if you see, just check if you are doing convolution between hn and xn, so you can see larger number of samples in hn, so more number of multiplication required for computing convolution, and more number of additions are required for computing convolution, so hence so it will not be efficient. Okay, so that's why take the minimum filter order. Okay, now we see the IR filter case. So the HZ is the real rational function of Z inverse. So here you can see you have a numerator polynomial, you have a denominator polynomial. Okay, so for this, when you are designing a IR filter, you need to keep this in mind whether it's stable or not. Stability must be ensured. Why we have not considered this point in designing the FIR filter? Why not? Why not we have discussed? Because the FIR filter is always stable, because the FIR filter's poles will always lie at origin, means they are inside a unit circle. If the quantization will not shift those filter coefficients. Okay, so that's one thing. If you are designing a IR filter, you can see here you have a denominator polynomial in Z inverse, and there may be some poles which may lie outside a unit circle. That should not be there, otherwise the filter will be unstable. So that's why you need to ensure the stability of the filter, because here you may there is a possibility of a filter of the solution of this denominator polynomial to be having magnitude more than 1. Okay, and the minimum of m or n that satisfies the design criteria must be used. Okay, now come to the cutoff frequency in digital domain. Generally, the specifications of a filter will be given in hertz, means the cutoff frequency may be given in hertz. Okay, but most digital filter are designed in normalized frequency range. Okay, so where normalized frequency, where you can say that's a omega, small omega, so that's from minus pi to pi, and the pi is corresponding to ft by 2, where ft is the sampling frequency. Okay, ft by 2 is the folding frequency, ft is the sampling frequency, and ft by 2 is a folding frequency, so the pi is corresponding to a folding frequency. Let's see, here you should keep in mind the suffix s is used, the suffix s is used for stop band. So okay, so we, in order to avoid the confusion, we are not using s suffix for sampling frequency, but for sampling frequency the suffix t is used. Okay, now the normalized pass band and stop band edge frequencies can be obtained from the linear frequencies as given below. Just see, when the filter specifications are given to you, the what will be given to you, the linear pass band edge frequency, linear stop band edge frequency, the sampling frequency, and all those things. So however, you need a normalized pass band edge frequency, normalized stop band edge frequency, so that can be obtained using this formula. This omega p is nothing 2 pi fp divided by the sampling frequency. Okay, and similarly omega is nothing 2 pi fs divided by the sampling frequency. So these are the normalized frequencies, omega p and omega s. Okay, so obviously omega is there, so these are the angular normalized frequency, I should say. For an example, so let's take this. Suppose we have the linear passband edge frequency of okay, of a filter, or specification is 3 kilohertz, and linear stop band edge frequency is 4 kilohertz, and the sampling frequency given to us ft is equal to 10 kilohertz. So we want to convert these frequencies to an angular frequencies. Okay, normalized angular frequencies. So you can apply the formula, and that's omega p will be 2 pi multiplied with fp divided by ft, so that will be give you 0.6 pi. Similarly, the omega s will be 2 pi multiplied with fs and divided by ft, so that's equal to 0.8 pi. Okay, and of course this ft, the sampling frequency, if you which is equal to 10 kilohertz, and this will be corresponding to 2 pi. As I told you, the pi corresponds to ft by 2, so 2 pi corresponds to ft. Okay, so that was what the cutoff frequency in a digital domain. So sometimes the frequency, linear scale frequencies are given to us, fs, sp, fp, ft. So what we have to do, we have to just translate it to an angular frequencies like this. Okay, now which one should we opt, FIR filter or an IR filter? Which one is better? What are the advantages of one over the other, or what are the disadvantages of one over the other? Okay, so there are several advantages to both types of filter. Let's see the advantages of FIR filter, and this is the disadvantages of IIR filter. First thing is, the FIR filter advantage is that it can be designed with exact linear phase in the range of in the passband frequency range. The other advantage is filter structure is always stable even with the quantized coefficients. Means the poles will are always at origin, so there is no point of instability of the FIR filter. Okay. The other thing is the filter startup transients have some finite duration. Disadvantages of FIR filter, or you can say it's an advantage of IIR filter. So the advantage of an IIR filter, suppose some specification of a filter is given to you and you are designing it using a FIR filter. So the order of the filter, suppose you are designing it using a FIR filter, so let's say the order of the filter is P. And if you're designing the same filter using FIR using IIR filter, say the order of that filter, if you design using IIR filter is Q. So in that case, the Q will be much smaller than P, or you can say the order of the IR filter is much smaller than P. That's why the order of the FIR filter is usually much higher than the order of the equivalent FIR filter meeting the same specification. Okay, so what does implies? It's the IR filter design. If you're designing it, so it's computationally efficient. Okay, or you can say the FIR filter is computationally inefficient. So this is an advantage basically. Lower the order, lower will be the complexity, computation complexity. Okay, so that's why IR filter can be preferred if you need less complexity. Okay, the other thing is the ratio. That's a typical figure basically. The ratio of the orders of typical IR filter to that of FIR filter is in the order of tens. Okay, the nonlinear phase of an IR filter can be minimized using a appropriate all pass filter. However, it again will lose its advantage of computational complexity. Okay, so computational advantage will be lost if we are using approximate all pass filter, which may discuss it when we will study the design of IR filter. Okay. The other point where we can use IR filter without concerning the linear phase basically. Okay, so in some of the applications where the computation is not real time, in some application where the computation is not real time, so the phase distortion is not an issue. Actually, there's no phase distortion, there's no concept of delay over there because it's not in real time. You have stored the data in memory, then doing some computation, then you can easily means the even there's no importance of the phase actually. So in that case phase is not an issue, so we can use that. Okay, like you can store some image in a computer first, then you're doing some processing of that to enhance, to filter that image. Okay, if you're not doing it in real time basically. Okay, so these are some advantages and disadvantages of IIR and F filter. Okay, now come to this basic design approach basically. The basic design approach for the FIR filter. FIR filter is based on the direct approximation of the specified magnitude response. Basically that's based on a specification. The magnitude response is specified, so we are trying to obtain the same kind of magnitude response. Okay, so that's just direct basically approximation of whatever magnitude response is given to us. Okay, with some additional requirement that the phase should be a linear phase. Okay, so the design for an FIR filter of order M must be accomplished by finding either the length m plus 1 impulse response, okay, samples of hn, or the samples of its frequency response h omega. Okay. So designing an FIR filter is nothing, it's finding its coefficient or finding the samples value of its impulse response, and or you can say the samples of its frequency response, and this frequency response should satisfy the specified magnitude response, approximately specified. Okay, let me clear this. Come to the IR filter design. So here the approach which we use, basically we can convert a digital specification into an analog prototype low pass filter specification. Okay, first we'll convert an analog digital filter specification to an analog prototype low pass filter specification. Then what we'll do, we determine the analog low pass filter transfer function. Means it's basically well established theory, or there are well established techniques of designing an analog filter. So what we'll do, corresponding to the desired low pass filter specification, we will design a low pass analog filter, not digital. Okay, the specifications are given for digital filter. What we'll do, we just first transform it to an analog filter, and that analog filter can be easily designed because that's sophisticated theories here behind this. Okay, then what we'll do, so basically when you are determining the analog function, that's the h big omega, point this big omega analog frequency. Okay, so then what your third step is, transform this h big omega into a desired transfer function of hz, then that we can just transform to a digital domain. So this transformation can be analog approximation techniques. Okay, okay, wait a minute here. I want to say that these analog approximation techniques are highly advanced, basically, and they usually yield a closed form solution. Okay, extensive tables are available for analog filter design, and many applications require digital simulation of analog systems. I'm just repeating to avoid any confusion. What we'll do, if some digital filter specification are given to us, we'll just transform those into an analog filter specification, then design an analog filter. So once the analog filter is designed, then that is h omega. Then what we'll do, we'll just transform this h omega into h z. This is your hz. Okay, and why we are doing, because there are some advantages of the many advantages actually of designing the filter in analog domain then transforming it. So that's all for today.